Good morning, grade 12 students. In this video, we'll continue the lesson about the introduction for the nervous system. And here in this slide, we're going to look at how to measure the speed of propagation of the nervous message. As you know, in physics, to calculate the speed, you have to find out the V, average velocity. Velocity is equal to the distance, delta D over the delta T, distance over the time. So distance is the difference between these two. This is called the delta D, distance over the delta t, which is the time. So here to calculate the velocity, velocity is equal to distance over time. So what are the factors that affect the speed of propagation of the nervous message in the nerve fiber? We have many factors that affect the propagation of the nerve fiber. One of these factors is the diameter of the nerve fiber. Here we have D1 and we have D2, nerve fiber 1 and nerve fiber 2, where D2 it's greater than D1. So if D2 is greater than D1, V2 will be greater than V1. So here, the as the diameter increases, or as the diameter of the nerve fiber increases, the speed of propagation of the nervous message increases too. So the first factor that affects the propagation of the nervous message is the diameter of the nerve fiber. As the diameter increases, the speed of propagation of the nervous message increases too. Moving now to the myelination of the nerve fiber. As we said yesterday, the myelination is an important factor that affects the propagation of the nervous message. So whenever we have myelin, these are the myelin here that are indicated in, let's say, in gray, for example. These are myelin. As we said yesterday, they are insulators and they have role in protection. So here they are the insulator, they are discontinuous. They have nodes here. So these nodes, they are referred to as nodes of Ranvier. As we said yesterday, the movement is going to be in a saltatory manner. So the propagation will be faster. So as we have a myelin, this is another factor for the propagation of the nervous message. So as the nerve fiber is myelinated, so the nervous message is going to propagate faster. So the nervous message will be accelerated. Okay, so till now, presence of myelin has higher effect on the speed of propagation of the nervous message than that of the diameter. So till now we have two factors. The first one is the diameter. So as diameter increases, the speed of propagation of the nervous message increases too. The second factor is the myelination of the nerve fiber. As the myelin exists, this means that we have higher or we have faster message or propagation is going to be accelerated asra, and the myelin has higher effect than that of the diameter. Propagation of the nervous message in the non-myelinated, it moves in this direction, while the propagation in the myelinated is going to jump over the myelin sheath. So, as we said, myelin, it acts as an insulator. It does not conduct a nervous message. As such, the message will be jumping over the myelin. So the nervous message will propagate in a saltatory manner, meaning that it's going to jump over the myelin sheath. That's why it's going to be faster, going to jump. Even though you are moving or jumping, jumping is faster. So here, that's why the message is going to be faster. Is a neuron always active? Are you always listening? I don't think so. Are we always walking? No. So here, are we always in pain? Sure, no. So here, is the neuron always active? The answer is going to be no. So do you always think? I don't think so. So a neuron or a nerve fiber is said to be active if we have a stimulation. And the neuron or nerve fiber is said to be at rest, meaning that without any activity, at rest in the absence of any effective stimulation. So let's move here. The aim of the following experiments is to study the electrical state of a neuron at rest. What did they do? I have an experiment one, the nerve fiber, and we have this needles of the voltmeter that are indicated on the outside, on the outer membrane of the nerve fiber. In the oscilloscope, this indicates zero, delta V. So a potential difference, delta V, it's equal to 0 millivolt. This means that the needle of the voltmeter did not deviate from zero, it stays at zero. What does this imply? This implies that there is no potential difference. This potential difference is the delta V. Okay? Potential difference is the delta V. So there is no delta V across the surface. Why? Because both of them they are found on the surface of the axon of the nerve fiber. So there is no potential difference at all at the surface of this axon. So this is the first experiment, delta V is equal to zero. Pay attention in the next, second, and the third experiment, what is the difference or the variable. In the second experiment, also the needle of the voltmeter did not deviate from zero. Why? Because both of them, they are placed inside the axon in the internal medium. Okay? And the delta V it remains at zero as shown here. So zero delta V. So this there is no potential difference in the internal, while both needles they are placed on the internal side of the axon. Moving to the third experiment. The third experiment, the needle of the voltmeter deviate away from zero. It moves toward minus 70 millivolt, as shown here also the needle of the voltmeter, minus 70 millivolt. So here, what can you deduce? Our deduction here is that we have a potential difference that exists between the internal and the external medium. So what can be deduced? The first deduction, a neuron at rest. Well, the meaning of a neuron at rest is not active, it's not acting, it's at rest. Okay, like it's in active mode. Since there is exists a potential difference between the interior and the exterior, as shown in the experiment of the nerve fiber, where the delta V is not equal to zero, it's said to be minus 70. So here they deduce that the nerve fiber at rest is polarized. The meaning of polarized, at rest, the nerve fiber is polarized, meaning that polarized has polarity is negatively charged, since it's equal to what? Equal to minus 70 millivolt. So the first deduction that at rest, the nerve fiber is said to be polarized. Whereas, since delta V is less than zero, so the internal or the interior of the nerve fiber is negatively charged with respect to the exterior. And second, the resting potential. What is the meaning of the resting potential? Resting is at rest. Potential is the potential difference that exists between the intracellular and the extracellular of the nerve fiber. So at rest, this is called the potential difference. It's called the resting potential. So the resting potential is the potential difference, it's delta V, that exists between the intracellular and the extracellular medium of the nerve fiber where at rest. So that's why it's called resting potential. Potential, it's the delta V that exists between the interior and the exterior of the nerve fiber, resting at rest. So this is the definition of the resting potential. Keep it in your mind. What the meaning of resting potential. So resting potential is the potential difference is the delta V that exists between the intracellular and the extracellular medium of the nerve fiber where at rest. That's why it's called resting potential. So moving to here, the resting potential. There is an electric charge across the membrane. We have ions. These ions, they are responsible for this potential difference. So the resting potential, when the cell is not firing, then it's not active, it's not working, it's equal to minus 70 millivolt. Is the difference between the interior and the exterior of the nerve fiber. So it cells, all the cells, they are not excitable cells, they have resting potential. They have resting potential, which is the electric difference between the intracellular and the extracellular. Almost this one is not constant, but in some species, it's minus 70 millivolt, like our case. Okay, so it's not constant, always minus 70. So note the resting potential, as I said, may range between minus 5 to minus 90, depending on the species and the nature of the nerve. So ions and resting potential. Ions, they are electrically charged molecules, like for example, the sodium, Na plus, potassium, K plus, fluoride, Cl minus, all of them, they are electrically charged molecules. The resting potential exists because of these ions. These ions, they are concentrated on different sides of the membrane, either the intracellular, like the case of K plus, or in the extracellular, like the case of K plus, Na plus and Cl minus. So Na plus and Cl minus, they are concentrated outside the cell, while inside the cell we have the K plus potassium ions. So here, concentration of Na plus. Let's have a look on this figure. This figure is showing the different concentration between the intracellular and the extracellular. This is the concentration of Na plus, the first one. Here in blue, we're talking about the extracellular fluid, meaning that the extracellular medium, cytosol, cytoplasm inside the cell. So here, concentration of Na plus. Concentration of Na plus is 15 millimolar, 15, while in the extracellular it's 150, so it's 10 times more. For here, we have K plus is 115. Here it's 5, so it's divided approximately by 30. Here it's 10, here multiplied by 12 times Cl minus in the extracellular. So here you have to show that we have different concentrations in the intracellular and the extracellular medium. So what is the origin of the resting potential? Resting potential exists due to the difference, as we see, in the ionic concentration between intracellular and extracellular. Why? Because we have difference in the membrane permeability. We have channels. These channels allow the entrance of some ions and blocks the entrance for others, or let's say reduces the entrance or others. So this is called the membrane permeability. So this membrane is permeable. It allows the entrance of Na plus, let's say, and it doesn't allow the entrance of K plus as much as it needed, for example. So here are differences in membrane permeability to different ions. For example, they are more permeable to potassium than for sodium. يعني بيخلوا البوتاسيوم أكتر يفوت من الصوديوم. So this is another cause or origin for the potential difference or the resting potential. This will lead a difference in the ions and difference in the electric current across the membrane, which is the origin of the potential difference. So we have two causes for the resting potential: difference in the ionic concentrations between the intracellular and the extracellular, as we see this in this figure, and also we have difference in the membrane permeability. For example, this channel allows the entrance of K plus more than Na plus. This channel allows the entrance of Na plus more Cl minus, let's say. So this is called the membrane permeability. How is the membrane potential difference? As you see here, we have 3 Na plus picked. Pay attention to this figure. Here we have the cytosol, 3 Na plus, they were picked. They enter inside cell. And then these 3 Na plus, they go out, and we have 2K plus, they enter. So here we lose one of the pluses. We have 3 plus, and these go, they come, instead of them, they come 2. So we lose 1 plus. This process occurs hundreds of thousands of times. So أنا عم بخسر 1 plus. عندي 3 كان Na plus. صار عندي بس 2 Na plus. So in the intracellular medium, we lost 1 plus. Imagine that this process will repeat itself hundreds of thousands of times. So that's why it's going to be polarized. It's going to be negatively charged. So 3 and A plus, they were pumped to where? To the extracellular fluid. And 2K plus, they were pulled or they were observed to the inside, where this requires the ATP. ATP is adenosine triphosphate, it's the form of energy used. So here, K plus, they enter inside the cytosol. So 2K plus, they are pumped inside the cytosol, and 3Na plus, they go out to the extracellular fluid. That's why we lost one of the positive. So here we can anti-platelet positive. Here we have only two positively charged ions. So membrane is more permeable to K than Na. Thus, the inside will be more negative. How is resting potential maintained due to the ionic distribution of the ions? So we have 3 Na plus out here at the extracellular. In the cytosol, we have 2K plus. So here we have 2 plus, here we have 3 plus. So here the extracellular will be more positive than the intracellular, and this will lead to the electronegativity and to the appearance of the resting potential, which is equal to minus 70 millivolt. Is the neuron always at rest? No, you will see. To keep in mind these terms, they are very important to know them before we start. So let's start first with the meaning of excitable neuron. The meaning of excitable neuron. Excitable neuron is the neuron that is able to respond to an effective stimulation. For example, hit my hand. Hitting my hand, this is stimulation. If it's effective, I will feel pain. So this is called an excitable neuron. Second definition was the meaning of action potential. Action potential, it's the term that's given to the electric visualization of the response of the neuron. For example, the electrocardiogram, you see these in the electrocardiogram whenever you go to the hospital, is the القلب and so on. So this is already the electrocardiogram. These are called, every one of these is called action potential. AP, action potential. Also, we have to keep in mind these definitions, what the meaning of threshold of excitation. Threshold of excitation is the minimum intensity of the stimulus that is able to stimulate a receptor and to emit a nerve impulse or message. Below this stimulus, there is no response. For example, my hand, it is a stimulus of 10 ampere, let's say. If it's less than 10 ampere, it won't respond. If it's 10 ampere and more, it would respond. So this 10 ampere is the minimum intensity that can cause an action potential or can cause a response. This is called the threshold of excitation. Also, we have upon excitation, there is the change and the potential difference across the interior and the exterior of the nerve fiber. هيدا stage in the potential difference, it should reach the threshold. If we reach the threshold, we'll cause an action potential. If it didn't, we won't reach an action potential. So threshold of depolarization is the minimum change in the potential difference that should be reached to create an action potential. This will be more explained and more clear whenever we reach to the experiment. Minimum time of excitation is the minimum time during which effective stimulation should be applied to cause an action potential. This will be explained more in this experiment. Action potential in the nerve fiber. Here we have, this is the resting potential. The final resting potential is equal to minus 70 millivolts. So here at rest, the resting potential is equal to minus 70 millivolts. While upon application of the stimulus of intensity I1. This is the intensity I1. I1 it's less than the threshold of excitation. So applying the intense simulation of intensity I1, there is no action potential. It remains at minus 70 millivolt, like this case of the resting. So here it's less than the threshold of excitation. So what will happen? There is no change in the potential difference, as nothing happened. Okay, so this stimulus is said to be ineffective. Why it's ineffective? Because it didn't cause the appearance of an action potential. Moving to the I2. Upon application of stimulus of intensity I2. Also, I2 is less than the threshold of excitation. It's less than the minimum time needed, minimum intensity needed to cause an action potential, or minimum stimulus needed to cause an action potential. But I2 here is greater than I1. Sure, we don't have the action potential. ما وصلت لشيء اسمه threshold of depolarization. So it increases a little bit, بنسميها شيء اسمه artifact. So here there is no action potential and didn't reach what? Didn't reach the threshold of depolarization. ما وصلت للthreshold of depolarization. Whenever it doesn't reach the threshold of depolarization, this means that there is no action potential. So here, as we see, slight change in the potential difference and the slight change in the delta V, it increases a little bit. Slight, it's called depolarization. Polarization is negativity. Depolarization, it's called hypopolarization. For example, if I said that this person is hyperactive, well, the meaning of this person is hyperactive, meaning that has higher activity than normal. While hypoactive is less than the normal. Its active activity is less than the normal. So hypopolarization, you have to keep it in mind. Polarization, it's negativity. A hypopolarization is decrease in the negativity. What does the mean of decrease in the negativity? It's moving toward the positive. So here we have hypopolarization, which is called this one, it's called the artifact. So this hypopolarization, it's due to the change in the potential difference, but it didn't reach the threshold of the polarization, the one shown in this line. So it's minus 50 millivolt. So did it reach the threshold of depolarization, then everything will go back and we will have nothing and we'll have no action potential. So the first important note you have to know it, that this potential difference should reach the threshold of depolarization. If it didn't reach the threshold, there is nothing change. So here you have to say that there is no change in the potential difference. As such, the stimulus is said to be ineffective also. While upon application of stimulus I3 greater than or equal to the threshold, either it's greater than or equal to the threshold. So here we have an action potential appears here. So what do you think about the intensity I3? It's effective or ineffective? It's called an effective stimulation. So it is effective stimulation. Here we have S as stimulating electrode, A as recording electrode, and B as the reference. And we show this on the oscilloscope where we show an action potential. So here I3, enough to change in the potential difference occurs that reaches the threshold of depolarization. What's the threshold of depolarization? So a response of action potential of amplitude 120 was recorded. So you can say that I3 is the first intensity to cause an action potential. So it's called a threshold of excitation, and also it's effective. It has both names. It's effective stimulation, since it causes the appearance of the action potential, and the threshold, since an action potential appears for the first time after this excitation. So they said 120 millivolt. Any one of you can explain to me why its potential difference of plus 120 millivolt? Yeah, waiting for your answers. Why it's 120? Raising your hands, please. Why it's 120 millivolt? Why the potential difference is 120 millivolt? Yes, let's move to Hariri. What do you think? Why it's 120 millivolt? Why is potential difference at 120 millivolt?
Because at the end it was plus 50 millivolt,
Exactly.
and it's
At the beginning, it was what? It was minus 70 millivolt, right?
yes,
Okay, so it came from minus 70 to what? To plus 50.
one
Here,
plus 50.
its potential difference is going to be minus 70 plus 50. No, we're going to remove the minus. We're going to be 70 plus
Plus 50.
So we move from 70 to minus 70 to 0. So we're moving towards the positive. So as approximation, and we remove the negatives, it's 70 plus from 0 to 50, it's 50. So 70 plus 50, so it's equal to 120 millivolt. That's why they said it's potential difference of 120 millivolt. Okay, thank you, Ali. So to continue, we have this idea about the threshold of excitation. So the first intensity to cause an action potential is called effective stimulation, and the threshold of excitation. Moving to I4. I4 also is greater than or equal to the threshold of excitation, while I4 it's greater than I3. So it's greater than I3. So we have here the intensity I4 is greater than or equal to the threshold. So here it's called an effective stimulation. So here we have appearance of the action potential. So it's called effective stimulation. So enough a change in the potential difference occurs that reaches the threshold. وصلت على threshold of depolarization, which always in this case it's minus 50 millivolt. So هذا بنسميه the threshold of depolarization. مجرد ما وصلت على threshold here, so meaning that it will fire an action potential, هيكون في عندي action potential. This action potential is going to be what of potential difference 120 millivolt. So as such, this I4 is said to be effective. Okay, Selena, why did I say only effective? Why didn't I mention that it's also threshold of excitation? Why do you think?
Because I3 was the threshold of excitation and
What
it's greater than I3.
I3 is called a threshold of excitation. Can you explain to me what the meaning of threshold? Why do we say threshold of excitation?
Because an enough change that
Because
it
it's the
reached
first,
the threshold.
because the threshold of excitation, Selena, is the first stimulation that causes an action potential. We call it threshold of excitation. Okay? So you have to keep it in your mind. Always the first stimulus that causes an action potential is going to be the threshold of excitation. The first one. دايما بنسميها threshold. After this, all of them that can cause an actual potential, they are called effective stimulations, like the case of I4. Here, the action potential in a nerve fiber, we have different phases. We have about 7 different phases of the action potential. Here, action potential in nerve fiber, we have the phase number 1. Phase number 1 is referred to as the resting potential, is equal to minus 70 millivolt. Number 2, what can you say about 2? Yeah, let's move to, what do we call this? Yeah, Badia. Number 2, we call about this, has a special name here. Number 2, it's called what? RT?
Uh, it's uh, it's artifact.
Artifact. Excellent, very good. It's called artifact. Here, whenever we talk about polarization, as I said before, polarization, I'm talking about negativity. So polarization, I'm talking about negativity. Okay? So polarization, negativity. Here I'm moving toward to the positive, away from the negative. So it's called hypopolarization. Why it's hypopolarization? Hypo meaning that decrease in the polarization. Hypopolarization, polarization negativity, hypo decrease. So hypopolarization is decrease in the negativity. Okay? Here, 3 is called depolarization. Number 4 is called inversion of the polarity. Number 5, we're going back to the polarity. So it's called re-polarization. Okay? Here, hyperpolarization is in the تحت threshold. And number 7 is going back to the resting state. Okay? So let's move to these phases. Number 1, as I said, is called the resting. So no stimulus was applied. Number 2, it's called the hypopolarization. Hypopolarization is referred to as artifact, but I prefer to use the word hypopolarization. Hypopolarization decreases in the negativity. Whenever we move to the positive at all, whenever it jumps from the negative to the positive, as shown in this number 3, so this is number 3 is referred to as depolarization. Number 4 is the state we're going to invert from the positive toward the negative. So it's called inversion of polarity. Number 5, we're going back to the negative. So going back to the negative, polarization. But going back, repolarization. Number 6 is called hyperpolarization. Why? It's hyper because polarity more than the normal. So it's more negative than the normal, even though it's more negative than the resting. And number 7, it goes back to the resting. Phasing of the phases of the action potential. So electrics understanding of the results. Depolarization. As I said, depolarization, so we move toward the positive. It corresponds to the hypopolarization of what? Of 120 millivolt. So we have 50 and we have minus times minus, so it's a plus 70. So it's 120 as Ali Hariri said before. And to reversing of the charges, they were negative and to become positive. What does this mean? This indicates that the interior of the nerve fiber becomes more positively charged with respect to the exterior, which becomes more negative. So the interior becomes more positive. So we move from the negative toward the positive. So this is called the depolarization. Re-polarization. Re, it's going back. Polarization, negativity. So going back to the negativity. So it corresponds to the return back to the initial state, where the potential difference will drop from plus 50 millivolt down to minus 70 millivolt. What does this mean? This means that the nerve fiber is again more negative where in the interior with respect to what? To the exterior, which becomes more positively charged. Hyperpolarization. Polarization, as I said, negativity. Hyper, increase in the negativity. So here, increase in the negativity is called hyperpolarization. So this corresponds to the increase in the electronegativity of the interior. It drops below the resting to the minus 75 millivolt. This means that the interior is now more and more electronegative compared to the resting. The resting was minus 70, while it's hyperpolarization, it's more negative than the resting. It is minus 75. Moving to understanding the ionic changes. At the resting at minus 70 millivolt, the cell membrane is highly permeable to K plus than to Na plus. What does this mean? This means that more K plus will be in the inside and more Na plus will be on the outside. More permeable to K plus, and it allows K plus to enter to the inside, and more than the Na plus will remain or on the outside. Depolarization, the membrane here we're talking about the ionic interpretation, okay? So the membrane permeability for Na plus increases, so more Na plus will open, and permeability to K plus decreases, so K plus channels, the channels that allow the passage of K plus, they close. So here more positive will be in the inside, and such it becomes more electropositive. So here this is the figure before depolarization, the more positively charged and more negatively charged. So what will happen? We have rapid depolarization since more positive will enter inside the cell. So entering of these Na plus inside the cell will move from the negative toward the positive. This is called the depolarization. Re-polarization is going back to the negative. So membrane permeability to Na plus decreases. So Na plus channels will close, the channels that allow the passage of Na plus, and K plus channels or permeability to K plus first increases. So the K plus channels open, so more positive charge will accumulate on the outside, not on the inside. That's why we're going to move to the repolarization and going back to the negative, since the anterior becomes more electronegative. So repolarization, as I said, sodium ion channels, they close. Repolarization going back to the negative. Depolarization triggers the opening of voltage gated potassium ion channels, K plus channels. So K plus rush out of the cell, repolarizing, and then hyperpolarizing the membrane. So here repolarization is going back to the negative, since the Na plus they will rush out of the cell and will be more positive accumulating on the outside of the cell. Hyperpolarization. Hyper is polarization more than the normal. So K plus channels, they are still open. They are too slow to close. So more positive will accumulate on the outside. The interior becomes more electronegative. Even more, it's more electronegative than in the case of the resting state. This is related to the phases of the action potential. Resuming the resting, potassium channels they will close, and then repolarization reset the sodium ions, and the ions diffuse away from the area. This is about the phases of the action potential. As I said, polarization, we have resting, it's minus 70 millivolt. Na plus channels, they open, they enter the Na plus inside the cell. So we have depolarization. Then repolarization, the K plus channels will open, Na plus will accumulate outside the cell, and Na plus will accumulate more inside the cell. And finally, number four, we have hyperpolarization, since we have more negatively charged accumulation in the inside of the cell. And finally, we'll go back to the resting and so on. What I want from this is to know the ions, the concept of, you don't have to study each single detail. I want you to study the concept of the different ions and the ionic concentration. Okay? So this is everything for our session today. Thank you.